Hi, my name is Sagar Adhikari, and this is my project for the analog electronics. The title of my project is the Overheat Warning System for the electronic device. I just made the all the components right now. So in this video, I will explain the simulation model and simulation results of my project. And the purpose of this project is to design a simple analog warning system that detects an overheat condition and activates an alarm output. The basic idea is to represent the temperature using an LM35 sensor model and compare that the sensor voltage with the threshold voltage and then generate an output that indicates whether the alarm should be on or off. Hi, I just opened the MATLAB and I'm gonna open the Simulink. At the Simulink, I need to create the blank model. Now I need to save my file as my project name. Project overheat warning system. Okay, we we create our file name is the overhead project warning system. Overhead warning system. Now at first I'm gonna add the essential component for my overall project. Let's first add the RAM block for the temperature input. Okay, we just added the RAM block. Let's rename this block as a temperature input. Temperature input. Okay, and then mm, let's set the. Okay, now let's input the gain block. Type the gain. Okay, here is our gain block. Sorry. Let's rename this gain block also. We call it LM35 sensor 35 sensor model. Okay, and then the other block we need is um, relational operation block. Now try the relational RELATI. Okay, here we go. Let's make it a little bit big. Now we need We need the constant block. Okay, we got the constant block. Now we need one more block for the scope. Yes, we added the scope. Now let's rename this scope as the LM35 voltage scope. Mm, LM35, LM35 voltage scope, LM35 voltage scope. Now just copy this scope and then we need one more scope. Okay, and then we need this scope for the alarm output scope. Let's rename this one alarm output scope. PE. Okay, now uh, we need one more block for display block. The display block is used to show the final alarm condition in the numerical form. Let's try the display. Okay, and the first one will work. Okay, after uh, we inserted all the components, we need to wire and connect each other components. Now, first I connect the temperature block to the temperature sensor model, which is LM35 sensor model. Okay, and then this one is connected successfully. And then I connect the output of the LM sensor to the input of the LM35 comparator. Let's rename this one for the LM35. LM alphabet COMPARATUR LM35 comparator. Now let's connect the output of the sensor to the input of the comparator. Now let's connect the threshold voltage block to the other input of the comparator. Now connect the threshold block voltage to the other input of the comparator. Okay. After that, I connect the output of the LM35 sensor to the LM35 voltage scope. I need to the output of the comparator to the LM35 voltage scope. Okay. And then I need to connect the output of the comparator to the alarm output scope. Now I can just branch this wire to the alarm output scope. Just click over here and then just connect this one over here. Okay. And then I need to branch the one more wire, the same wire to display wire. Let's rename this one for the display also. D- Display enough. Now, uh, now I need to set the constant value, and then everyone, let's first start the ramp. Okay, I set the slope to 0.3, the start time to 0, and the initial output to 25. Okay, I use this value so that the simulation start at the 25 degrees Celsius and the temperature increases gradually with the time. Now I'm gonna set the gain parameters. I set the gain value to 0.01 and keep the multiplication factor as a element wise. I use the gain value of the 0.01 because of the LM35 sensor give an output of the 10 millivolt. Sorry. Yeah, element wise, it gives the output of the 10 millivolts per degree Celsius, which is equal to 0.01 volt per degree Celsius. Now we're gonna set the relational operator. I set the relational operator to greater than or equal to, this one is greater than or equal to. I use this condition so that the alarm output becomes active when the LM35 sensor voltage reaches or exceeds the threshold voltage. Now I'm gonna set the threshold voltage. Let's rename first. This one block is the threshold. Okay, threshold voltage block. Threshold voltage block. Okay, I'm gonna set the value to 0.40. Okay, I use this value because 0.40 volt corresponding to about 0.4 volts corresponding to about 40 degrees Celsius for the LM35 sensor, and this is used as the threshold for the alarm condition. Then okay, now we already added the scope, and we added the alarm output, and we added the display enough, and then we already connect all the blocks using the wire. Now I'm going to set the step time to from 10 to 100. I set the simulation step time to 100. I use these values so that I can see clearly observe the increase in temperature input, the LM35 voltage response, and the final alarm output behaviors. Now let's run the simulation. Uh, okay, here is the LM35 voltage curve. Let's open one more time. Sorry, we connect it wrongly. Just delete the wire and connect this wire to over there so that we need to run one more time. Okay, let's check the LM35 output voltage. Okay, this one is the output voltage curve. In this graph, the LM35 voltage starts at the 0.25 volts, 0.25 volts over here, which corresponding to the 25 degrees Celsius. Then it increases gradually with the time as the temperature input temperature increases. Around 50, almost around 50 second, and the voltage reaches about the 0.40 volts, which is the threshold voltage. By the end of the simulation, the voltage reaches about the 55 volts. Yeah, by the about around 50 seconds, almost 50 seconds, it reaches to 0.40 volts. And then at the end of the simulation, it reaches about 55 volts. This is very good data. Now, let's check the alarm output scope. Okay, here is the alarm output scope. Here, the alarm output scope output remains 0 at the beginning. Here you can see clearly, which means the alarm is off. Uh, Around 50 second, almost about 50 over here, the output changes from the 0 to 1. This happens because the LN35 voltage reaches the threshold voltage of the 0.40 volts at that time. After that, the output stays 1, which means the alarm remains on. Now, let's check the display. Now, I observe the alarm on-off display. The display shows the final value as 1, which means the alarm is on. This confirms that the system has entered the overheat condition. So, in conclusion, the simulation shows that the overheat system worked properly. The temperature input increases gradually with the time. The LM35 sensor model converts it into the proportional voltage. Once the sensor voltage reaches the threshold value, the alarm output on. Okay, and thank you.